Today we're going to talk about how to evaluate and graph polynomial functions. So some of this should be review. We're going to talk about vocabulary first. Degree. The degree is the exponent on the variable in a term of a polynomial in standard form. The degree of a polynomial is the highest exponent on the variable of a term in standard form. And the standard form of a polynomial is when the terms are in descending order from highest to lowest by degree. So this is just the general polynomial function. And of course it says where n is a non-negative integer and the coefficients a(n) and all the way up to a sub 0 are real numbers. So these are just coefficients in front and this is just a constant. So for example, we have this polynomial function. Notice that it has this as the leading term. This is the leading term because it is the highest power for this term. This is a cubic term because it's x to the third power. This is a quadratic term because it's x squared, linear, and this is constant because x to the 0 power we don't write. For this, notice that the leading coefficient is the number in front of highest term degree. So this is the leading coefficient of this entire polynomial because it's the number that is in front of all of them. And of course we said that this was degree 3, 2, 1, and when there is no x 0. And the degree of the entire polynomial is 3 because it's the highest when we were in standard form. Polynomials are classified by the degree and number of terms they contain. So that's how we classify them. A polynomial with one term is called a monomial. A polynomial with two terms is a binomial, and a polynomial with three terms is a trinomial. Polynomials with four or more terms we just call a polynomial. And so let's go ahead and use the chart below to summarize the names assigned to polynomial by its degree. So for this first one, we have f of x equals 6. There is no x there. So when there is no x, it's really like saying we have x to the 0 power, because remember something to the 0 power is just 1. So the degree is 0, which we call constant. Number of terms that we have, there's one term. And of course, one term means it's a monomial. So we would actually call this a constant monomial. So that would be the name of the entire function by the degree and the number of terms. So the classification. So then for the next one, we have f of x equals x plus 3. So the highest power of x is to the first power. This is in standard form. So that means this is, of course, we know linear when we have a degree of 1. There's two terms, so this is a binomial. So the classification for this one would be a linear binomial. The next one, we have 3x squared. So the degree of this is the power 2, so this is quadratic. You all did a lot of quadratic equations last year in Math 2. And so the number of terms, there's one term. And again, terms are separated by addition and subtraction signs if you forgot. And so this is a monomial. And so this is called a quadratic monomial for the classification. This one has 1, 2, 3 terms, and the highest power is a degree 3, so this is cubic. There's 3 terms we said, so trinomial. So this is a cubic trinomial. For the next one, we have degree 4, which is quartic. And so for this one, there's two terms, so binomial. So this is a quartic binomial. Here, this is in standard form again with degree 5, so this is quintic. And there's four terms, so that means it's a polynomial. We have four more terms, so we call this a quintic polynomial for the classification. Anything above degree 5, we just write degree 6, degree 7, degree 8. These are the names that you do need to know along with the terms. And so again, this is the classification of each of these polynomials. So let's go ahead and talk about what a polynomial is. Polynomials do not have the following. So polynomial does not have negative exponents or exponents that are not whole numbers. So remember, whole numbers we know are 0, 1, 2, 3, etc. So no fractions or decimals. So if I have x to the negative 2 power, remember that is equal to 1 over x squared, so we can't have a negative exponent. We also cannot have a fraction exponent. X to the 2/3 powers is equal to the cube root of x squared. So again, no negative exponents or exponents that are whole numbers. And again, that's because we can't have fractions or decimals. Which means then if we can't have that, there's no variables in the denominator. So we can't have a variable underneath a radical sign. So that was over here. So again, the fourth root of x, the square root of m, those are all radicals. If we had the cube root of, again, x to the 5th power, even if we simplify that, it's still a radical. And it can't have a variable exponent. So if we have 3 to the power of x, this is not a polynomial. Why not? Because when we have a variable exponent, remember this is an exponential function. Okay, so decide whether the function is a polynomial function. If so, write it in standard form, state its degree, type, and leading coefficient. So for this first one, if I look right away, I see the 2.5 as a power. So that term right there tells me that this is not a polynomial. Because remember, we can't have decimal or fraction exponents. Over here, this is a polynomial. Even though we have a decimal, that's a coefficient, not an exponent. So that's okay to have a coefficient as a decimal or a fraction, just not the exponent. So that means we just need to write this in standard form. This is degree 4, degree 1, and degree 2. So standard form, remember, means you write it from highest to lowest degree term. So 9x to the 4th plus x squared plus 3.7x. So the degree is 4 because that's the highest term power. The leading coefficient is 9 because that's the number in front. And this is called then, if it's degree 4, a quartic. And there's 1, 2, 3 terms, so quartic trinomial. For this one over here, so this one has a square root, but there's no variables underneath the square root. So again, remember over here, we said you can't have a variable as an exponent, a variable underneath, and no exponents or exponents that do not have whole numbers. So here, a square root with just something with a number that's numerical is okay. And so for this, we can rewrite this in standard form. This is degree 3, degree 0, and degree 2. If you want to write that square root of 5 in front, you can. If you want to write like this, just make sure that it looks like the x is not underneath the square root. So minus 2x squared plus 7. So for this one, this is a degree of 3, and leading coefficient is the square root of 5. And so this is cubic. There's 3 terms, so again, a cubic trinomial. So the next thing we want to talk about is the end behavior of a polynomial. So this is important because we're going to be using this a lot. So the end behavior of a polynomial describes the behavior of the graph as it becomes infinitely large and infinitely small. So this is what happens to the ends of our graph. So in the long run, as we get towards infinity in the positive direction and infinity in the negative direction, what is my graph going to look like? So the end behavior of a polynomial function can be determined from the characteristics of the lead term. The lead term will fall into one of the 4 categories based on the degree of the polynomial and the leading coefficient. So that's what will help us to determine what the end behavior is using that lead term of a polynomial, which is why it's important to know how to put your polynomial functions in standard form. So here are the 4 different categories that we have based upon the leading term. We have degree odd and coefficient negative. So if I have an odd degree, think about y equals x to the first power. We don't write the 1, but that's an odd degree. And it says the negative leading coefficient. So if I put a negative in front, that would be odd degree with a negative leading coefficient. So think about what that graph may look like. We know what something linear looks like. If it's positive, we know it goes up to the right, but a negative slope, so like if we have y equals negative x, we know our graph goes like this. So look at the ends of your graph. As we get closer and closer to infinity, which is going to the right, our graph goes down. If we go towards negative infinity, our graph is going up. So we're looking at the ends of our graph and what are they doing. So odd, negative for the leading coefficient. Again, we're looking at the leading coefficient and the degree means that it goes up to the left and down to the right. So as x approaches negative infinity, y approaches infinity, and as x approaches positive infinity on this right side, we're going towards negative infinity. Do we have to have y equals negative x? No. Let's do y equals negative x cubed. So let's go ahead and look at this in our calculator. If you don't remember, we just talked about cubic functions the other day and we looked at the graphs. So if I hit graph here, notice again, our graph is up to the left and down to the right. Even if we did a negative x to the 5th graph, our graph will still be up to the left, down to the right. Even if we were to add other terms, it doesn't matter because remember we said that the end behavior is determined by the highest power of x. So that means the highest power of x is x to the 5th. So your leading term and the negative leading coefficient. So if I hit graph, even with that, it will in the long run still be up to the left, down to the right. If I did x to the next odd power would be 7th power. And if I did that, again, my graph will be up to the left and down to the right. So that is true of any degree that is odd with a negative leading coefficient if we're talking about, again, the end behavior of a polynomial function. So it'll always be up to the left, down to the right, and this is the notation. So if we have a degree that's odd positive, we'll think about the smallest positive degree that we have at y equals x. Again, that's to the first power. Think about what that graph looks like. So here's the graph of y equals x. Up to the right, down to the left. So as x approaches positive infinity, y approaches infinity. And as x approaches negative infinity, y approaches negative infinity. And that will be true of any odd power of x with a positive leading coefficient. So y equals x cubed, y equals x to the fifth, y equals x to the seventh. And again, even if we add other degrees that are less than the highest odd power with a positive leading coefficient, it still will be down to the left, up to the right. That just changes what happens in the middle when you have a higher power and other terms added to that. So the next one we're going to look at is what happens then when it is an even positive. So when you have a degree that's an even positive, think about your smallest even degree too. So y equals x squared. What does that graph look like? So if we think about this graph, y equals x squared, we did a whole bunch of quadratics last year, we know it looks like this. It has a parabola shape and both ends are going up. So both the left and the right go up. So as x approaches positive infinity, y approaches infinity, and as x approaches negative infinity, y approaches positive infinity. You could also write this together, so you could just write this as x approaches plus or minus infinity, y approaches infinity. That would be okay to write too. Either way, you can write it separate or together. So even if I had y equals x to the fourth, both ends would still go up. Y equals x to the sixth, x to the eighth, anything with a positive leading coefficient and an even degree. So if the leading coefficient is negative and even, so think about your smallest even again with a negative leading coefficient, y equals negative x squared. We know when we have that negative, it makes our graph reflect across the x-axis or open down. So that means both ends would be going down towards negative infinity. So as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches negative infinity, or you can write it all together as x approaches plus or minus infinity, y approaches negative infinity. Now some of these I wrote the negative before the positive for the x as it's approaching. As you can see, I did the negative and the positive. Doesn't matter what order you write it in. Usually students like to write it from left to right, so negative infinity and then what happens there. So these are the four possibilities. So that's why it's important to know how to put your polynomial in standard form and how to classify it. So what is true about the degree and leading coefficient of the polynomial function whose graph is shown? Write the end behavior of the graph using the correct notation. So go ahead and take a moment to pause the video and do these on your own. When you're done, unpause and we'll take a look at it. So if I look at this first graph, the first thing I would notice is that both ends are going down. Since both ends are going down, if we look at our little chart where what happens when both ends are going down, we can see that it's going to be even degree with a negative leading coefficient. So this is an even degree with a negative leading coefficient. And so what do we know then for the end behavior as x approaches plus or minus infinity, so either side, your y values in the long run will go towards negative infinity. Looking at this next one, this ends up, this one's down. So when they're opposite, you know it has to be an odd degree. And when this side's up and this one's down, think about your smallest power x. Y equals x goes this way, so y equals negative x. That means it's a negative leading coefficient. And so this one we do have to write separate as x approaches values towards negative infinity. So this side of my graph, your y values go towards positive infinity. And as x approaches positive infinity, so now the right side, your y values are going down towards negative infinity. Looking at this one, again, they're opposite, but now the right end's up and the left end's down, so this is an odd degree with a positive leading coefficient. So as x approaches negative infinity, your y values go down towards negative infinity. And as x approaches positive infinity, your y values go towards positive infinity, so up to the right. And the last one, both ends are up, so that means this has to be even because they go in the same direction. So this is an even degree with a positive leading coefficient. And as x approaches either plus or minus infinity, your y values in the long run would go towards positive infinity. So those are the four scenarios that we just talked about, looking at the graphs and writing them out. This next one says, describe the end behavior of the following functions, then identify the x and y intercepts. So if we look at number 8, if I want to determine the end behavior, I would need to figure out what the degree and leading coefficient are. So before we do that, let's go ahead and look at the x-intercepts. So recall the x-intercept. How do we find that? So you find the x-intercepts by setting what equal to 0. So remember, you set y equal to 0 and solve. How do you find the y-intercept? You set x equal to 0 and solve. I should say and solve for x here, and this one you solve for y. So if I set y equal to 0 to find the x-intercepts, I get 0 equals x minus 1 squared and 0 equals x plus 1 squared. You can set them both equal to 0. To get rid of the square, you take the square root. So what's the square root of 0? Just 0. So we don't really need to write that power. And then you solve. So here I add the 1, so I get x equals to 1. And over here subtract the 1, so x equals negative 1. So x equals 1 and x equals negative 1. So how do I find the y-intercept? So the y-intercept, you set each of your x values equal to 0 and solve. So y is equal to 0 minus 1 squared times 0 plus 1 squared. 0 minus 1 is negative 1, and negative 1 squared. Remember, if you have an even power with a negative, it becomes positive if you're squaring that negative. So that's 1, and 1 squared is just 1. So that means that y is equal to 1. So the y-intercept would be 0, 1. For this, remember to find the end behavior. The end behavior, as again, is going to be found by the characteristics of the lead term. How do you find that? It has to be in standard form. So to find end behavior, it must be in standard form. So this is not standard form because you don't have all the terms FOILed out, combined like terms, so no parentheses. So if we thought about multiplying this out, think about what the highest degree would be. So really this is saying we have x minus 1 times x minus 1 times x plus 1 times x plus 1. So you don't really need to multiply this all out to find the end behavior, but you can just think about multiplying out. If I multiplied all the first terms together, x times x times x times x, well, what happens when you multiply something with the same base? You add the exponent. So 1 plus 1 plus 1 plus 1 would be x to the 4th power. And what's in front of all the x is 1. So 1x to the 4th power is the leading term. So that means this is a degree 4, which is even, and the leading coefficient is 1, which is positive. So this is even positive. So what happens with even positive? Remember, both ends go up. So as x approaches either plus or minus infinity, your y values go towards positive infinity. So let's go ahead and do over here. The x-intercepts. So set each factor equal to 0. And solve. So here we get x equals -2, x equals subtract the 1, -1, and x equals add the 3, so +3. So x equals -1, x equals -2, and x equals 3. So the y-intercept, we're plugging 0 in for x. So we get 0 plus 2, 0 plus 1, and 0 minus 3. So that means we get 2 times 1 times -3, which gives us -6. So 0, -6. So the end behavior, if we were to think about multiplying this out, x times x times x would be x cubed. And what's in front of the x is 1. So if you multiply 1 times 1 times 1, you get 1. So this is the leading term. So this is degree 3, which is odd. And the leading coefficient is 1, which is positive. So that means if it's odd, positive, think about your small solid positive. The right end goes up, left end goes down. Think about y equals x. So that means as x approaches negative infinity, your y values go towards negative infinity. And as x approaches positive infinity, your y values go towards positive infinity. All right, so let's go ahead and take a look at the graph. So graph each of the polynomial functions, identify the domain range x and y-intercepts, local extrema, and the end behavior for each function. Remember, local extrema just means the maximum slash the minimum values. All right, so to look at this, we're going to go ahead and use our calculators to help us. So we're going to go ahead and plug this into our y equals on our calculator. We're going to learn how to do these without our calculator eventually, but for now we can use our calculator. Negative x to the 4th power minus x squared plus 20. So if I hit zoom 6, which is a standard window from -10 to 10 for x values and -10 to 10 for y values, I know that this is not a good window because I don't know which way my graph's going. So if I look at my equation, I see that this is a degree 4 because this is in standard form. So that's the highest term right here. And that means this is even. And the leading coefficient is -1, so even negative, which means both ends should be going down. So if both ends should be going down, that means that I'm not seeing the top of my graph. So I'm going to go to my window and make my y maximum maybe larger. So let's try 30 and hit graph. So when I do that, now I can see that there is a maximum there. So if I'm graphing this, I'm going to actually find that maximum using my calculator, second trace. If you go to number 4, which is maximum, and we did this in our quadratics unit in Math 2, so left bound means something to the left, then use your right arrow to go right bound, something to the right. Notice you see these two arrows. So for guess, that means that your calculator is going to calculate where the middle is in between these two arrows. So always make sure they're pointing at each other. So notice that the maximum says 2.3058 e to the -6. Well, we'll look at where it's at. E to the -6 means times 10 to the -6. That means you would be taking this decimal place and moving it to the left 6 times. Sometimes the calculator does that instead of writing 0, just the way that it happens. And so really this is just 0 and 20. So that means we have a maximum of 0, 20. So go ahead and take a minute to graph the graph on here. Well, if we want to graph the graph on here, then we also probably want to know what the x-intercepts are. So remember, to find the x-intercepts, you can do second trace and use your 0 function. So if I want to find something to the left of the 0, that would be below the x-axis. Something to the right is above. Notice again that value should be in between the two arrows pointing at each other for guess, and hit enter. So we get -2 on this side, and then you have to do it again. Second trace 0, and now I need to go to the other side. Something to the left bound is now above the x-axis. Same thing to the right bound would be below. Enter. Again, the two arrows are pointing each other, so that's in between. Enter. And I get 2, so 2 and -2. And we want to find the y-intercept. Well, we already did that. We have the maximum at 0, 20. You can double check, hit second trace value, and plug in x value of 0. Notice you get 20, which is what we said was our maximum. And so those are the values that we're going to use in order to help us graph. So on my graph, I'm going to count by ones on the x-axis. So this would be 1, 2, 3, 4. And on my y-axis, because it has a y-intercept of 20, I'm going to count by 5. So 5, 10, 15, 20, 25. So here is my y-intercept and my maximum. And I cross here and here. And so my graph has both ends going down. What's the domain? We can plug anything in for a polynomial function, so all real numbers. The range would be -infinity because it goes from here up to here is the highest. So -infinity to 20 bracket. So what's the end behavior? As x approaches -infinity, your y values go towards -infinity, and same thing as we approach +infinity, our y values go towards -infinity. Again, if you write f of x or y, it's the same thing. And so why don't you guys go ahead and pause the video, do the next one on your own. When you're done, you can unpause to check your work. So I went ahead and put it in my y equals, and if I hit zoom 6 for, again, a standard window, -10 to 10 for x and y values. If I go back to my equation, I can see that this is in standard form, and this is the leading term. So this is a degree 3, which is odd, and the leading coefficient is 1, which is positive. So odd, positive means the left end's down and the right end goes up. So if I go back to my graph here, it's hard to see the right end because I can see it crosses the y-axis, which is something that I need to find. So I'm going to change my window just a little bit. So maybe for my y maximum, I'm going to go to 20. And that's what my graph looks like, which makes sense because it looks like a cubic function. It's just the other stuff tells us that it's doing different kinds of transformations to our graph. So for this, for my x-intercept, second trace, 0. And if I scroll here, so the left bound would be below the x-axis, right bound would be above. And again, notice that my 0 is in between the two arrows pointing at each other, so enter for guess. So we get -2. To find the y-intercept, I can hit second trace value, and y-intercept's x value of 0, so 10. So I have my x and my y-intercept, so my x-intercept, so my x-intercept is at -2, y-intercept was 0, 10. Domain, all real numbers, and the range was also all real numbers. And so for this, we can just go ahead and count by 1 on the x scale. So 2, 4, -2, -4. So this was my x-intercept. My y-intercept goes up to 10, so I'm going to count by 2. So 2, 4, 6, 8, 10. So it hits right here. So my graph resembled a cubic function. So for this, degree is odd, positive, so right end's up and left end's down. So remember, it looks like that. So as x approaches -infinity, your y values go towards -infinity, and as x approaches positive infinity, they go towards positive infinity. And that's it for analyzing the graphs.